Hello everyone, Mr. Fritz here. We're going to talk about probability trees and sampling today. So let's dive right in. Tree diagrams. Well, you've seen these before when you were sampling, but let's talk a little bit about how to use them for probability, specifically probability. So tree diagrams can be used to illustrate the sample space. That's what you've done. If the possible outcomes are not too numerous, you usually don't want to use tree diagrams. We're talking about like thousands of possibilities, but usually when we're on the order of I don't know, 6 to 24 or so. Once the sample space is illustrated, the tree diagram can be used for determining probabilities. We'll talk about how to do that. So consider you have two archers firing simultaneously at a target. These are independent events. One person's shot does not affect the other person's shot at all. We have one person, Lee, has a probability of 3 out of 4 of hitting a target, and another person, Yuka, has a probability of 4/5 chance of hitting the target. So we can actually diagram this information, and we can make a tree that branches out to illustrate these two separate probabilities. And we'll also mark the diagram. An H would mean a hit, and an M would mean a miss. And so we could start off, the first branch would be the first archer. So every single iteration or every single stage of these tree diagrams should be one of the events that occurs. So in this case, one event is Lee's shot. And so we can illustrate Lee's results with a 3/4 probability that there will be a hit and a 1/4 probability that there will be a miss. Next, we have to take a look at Yuka's results. So off of this possibility from Lee's hit, there could be a hit that follows a hit from Yuka, or there could be a miss from Yuka. That both of these possibilities stem from the hit from Lee's arrow. But similarly, you can have the same two outcomes happen branching off of a miss from Lee's results. So when we show these branches that come off of each of these items, what you're going to see is we have some repetition going on. So it's no coincidence that we have the same branch here as we have here. It is because that is the independent event that can occur after the result of that first event. So what we have is we have these outcomes. Here, the ends of all these branches, or the tails, have all of the possible outcomes for this entire two events. You can have a hit followed by a hit followed by a miss followed by a hit, and a miss followed by a miss. This looks a lot like the heads and tails and die tossing probability trees that you've already done and seen. But what's a little bit different about this is that we have different probabilities. It's not just 1 out of 2 or 1 out of 6, but we have these 3/4 chance times a 4/5 chance. Remember earlier we talked about when you have compound events, if you have something and something, you want to find the probability of a hit and a hit. What you do is you end up multiplying those individual probabilities together. So that's what's going on over here. This is the probability of Lee getting a hit times the probability of Yuka getting a hit. And this would be the probability of Lee getting a hit times the probability of Yuka getting a miss, and so on and so forth. So that's why we're multiplying those things together. What I also hope you notice is that if you add up all of these compound probabilities, we are going to actually find that that does total equal to 1, which should make sense because these are all the possible outcomes. So this is like saying the chance of n outcome occurring should become 1. So that's why that sums to 1. Some other things to take a note on. The probabilities for hitting and missing are marked on the branches. This is just kind of the structure for these tree diagrams. We'll indicate the probabilities. And this becomes important when we're not talking about just 50-50 chances. Before, when you've seen these tree diagrams, there was an equal probability between each branch. That's not always the case. In this case, there's a 3/4 chance that I'm going to land on this branch or this limb, and then there's a 1/4 chance I'll land on this limb. So when that's not 50-50, we want to illustrate that. There are 4 alternative branches, and so that's showing a particular outcome for all these scenarios. So every single end represents a path towards one outcome. So if I looked at one of these branches at the end here and I said, well, how did I get here? I got there from taking a head, then a head, and that's where my hit outcome comes from. Another thing to note is that all of the outcomes get represented by the end of this tree diagram. And then finally, the probability of each outcome is obtained by multiplying the probabilities along its branch. And again, that's because of that probability law that says if I want the probability of A and B, and these are independent events, this is going to equal the probability of A times the probability of B. So this is same stuff as you looked at in the last series of videos. All right, so let's talk about an example here. We have this guy, Carl, and Carl's not having much luck lately. Too bad, Carl. His car only starts 80% of the time, and his motorbike will only start 60% of the time. So we want to draw a tree diagram to illustrate this situation. The first thing I might say is what are the independent events that are going on? Well, we have the chance of his car starting, that's 1. And then we have the chance of his motorbike starting, that's 2. So each of these events gets a section of branches. So why don't we start off with our tree diagram here, and we'll start off with the event of the car starting. So there is an 80% chance, or let's say a 0.8% chance that the car will start. And so let's say it is a S, or for a start or success, for a 0.8% chance of the car starting. And then the chance of it not starting, this should make some sense. If I have an 80% chance of it starting, there is a 20% chance, or a 0.2% chance, that it will not start, or we'll say fail. And this is also because I want you to kind of keep in mind that we're talking about complementary events. The probability that either of these things should happen should be 1, and these are in direct comparison or direct contrast to one another. So what I'll say is this is the chance of it starting, this is the chance of it failing, and I'm just going to say this is the car right here. So the next event is the motorbike. Out of the starting branch, there is a 60% chance that the car will start, and so then there's a 40% chance, that the motorbike, there's a 40% chance that the motorbike will fail or not start. And then we have the same pair of branches, 0.6 for starting and 0.4 for failing, coming off of the failure of the cars starting. So I'm going to actually indicate that with the motorbike. So this is what each of these sections represents. This is the car, this is the motorbike. So there's my tree diagram. Let's use this tree diagram to determine the chance that both will start and that Carl can only use his car. So for that first piece here, if I want to know the chance that both will start, let's look at which of these 4 outcomes illustrates both of them starting. And the only way that I can get there is if I follow this series of branches, if I start both of them. Well, so I want to find the probability that the motorbike, or that the car will start, and the motorbike will start. So that's going to be given as the probability of the car starting times the probability of the motorbike starting. And so that's going to be given as 0.8 times 0.6. So the total probability for this guy is 0.48. That is the probability, a little less than half chance that both of these things will start. All right, so let's take a look at the next question here. We want to find the probability that Carl can only use his car. So, I guess we have to do a little bit of thinking about this. What does that mean if he can only use his car? If he only uses his car, that means that his car was able to start, but his motorbike was not. So I'm looking for the probability of the car starting and the motorbike failing. So that's going to be given as the probability of the car starting times the probability of, and you know what I'll do is I'll call this, instead of probability of M, since probability of M means that it'll start, I'll say this is the probability of not M, giving it that little apostrophe. So I want the probability of the car starting times the probability of not the motorbike starting. And that's going to be illustrated by this path right here. This is going to force Carl to use his car if only the car starts. So this will be given as 0.8 times 0.4, which is going to be given as 0.32. So he has a greater chance that both of these things will start. So even though he's a little unlucky, he still has a better chance that both of them start than just the car. So using this tree diagram, we can illustrate all these probabilities. And again, the purpose of doing these tree diagrams is just to visualize what's going on here. So this is a helpful visual to see all these outcomes, since I think it can be kind of tough to keep all this in your mind at once. So why don't you try this example kind of like this. I have for you a started off tree diagram, and I want you to pause the video and complete the problem, copy and paste the tree diagram, or copy and rewrite and complete the tree diagram, and then answer these questions about the tree diagram. So pause the video, give this one a shot. All right, and here are my solutions to this one. I've completed this tree diagram as follows. The important thing to note is that even though the 40% chance of this branch wasn't illustrated, it is the complement to this 0.6. So that's where that 0.4 is coming from. It's given as 1 minus 0.6. And then the 20% and the 30% are given to, and the same two options are also complementary. So that's kind of where you're piecing together all those other pieces of the question. So hopefully the tree diagram you're seeing can serve multiple purposes, not just for heads, tails, or dice throws, things like that.